Let's all camp at the professor's office hours today. Just open at 4. No, his office hours are on Wednesdays, though. No, it's on Thursday, right? I click Thursdays. Next time we might have ice check. Office hours today or Tuesday? Your office hours.
Mine are today.
Oh, they're
Yeah.
no, all you do is today. That's all. That's
Yeah.
all happening here.
Yeah.
Professor, what? Where do you go? They're 4 to 6, right?
Sorry.
4 to 6.
4 to 6. Yeah. Yeah.
Completely have the wrong thing.
I had it initially on Tuesday. I updated it like last week. It was
Perfect Thursday.
So I know if the slides might have some inconsistent information, but use Canvas, the homepage. That's the very last, latest. Yeah. So can everyone hear me at the back? Yeah. Can everyone hear me at the back? Yeah. Let's get started. Have you guys started the assignment? How's that going?
Brutal.
Brutal? No, it's not too bad. It's not too bad. What's the hardest question, or what are the hardest questions? Sort of. The Gaussian.
Yeah, I think it's around like 1.3 and 1.4.
Yeah.
And maybe not. I'm not sure about 2.
So you can move ahead, like don't get stuck on those. Continue finishing the rest, and you can come back to those. We added those questions like this year, so just to get it a bit more interesting. But so yeah, like don't get stuck on them. They are hard, yes. But I thought it'd be good to sort of like get all of you like kind of familiar with like these key concepts in probability statistics and the linear algebra. So essentially, because we don't have time to go through too much in depth in the class, so. This was good. A few question.
Yeah, for the linear algebra.
Yeah.
Are we supposed to do everything by hand, or can we just use NumPy?
So by hand. By hand. Yes. 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 Yeah. You'll find in the very last question, so you can do everything by hand apart from maybe the very last question with the SVD, with the single value decomposition. So we'll clarify on that, but everything else should be done by hand. So you should be able to do it. So I spoke to my TAs. We have a few news announcements. So we're extending the deadline to the 5th of October, so 2 more days for this. It's basically because we cannot. You had around 10 days, but I cannot extend more than that because we had the next assignment afterwards due. So you'll have another 10 days afterwards for assignment number 2 in that case. So we cannot shift the assignments like that. We have a late day policy though. So for example, if you need to use, for example, like some late days, for example, like you have a maximum of 5 in total throughout the course. Do use them somehow smartly. This is in the syllabus, so you can use them for this assignment, for assignments 2, 3, 4. But those assignments might get even harder. So make sure you save some of these late days for when you need them. If you have especially medical circumstances, some very special circumstances, we can decide individually. So email my TAs for that. So they'll decide, and like they will discuss with you and decide if you get any extra days. But otherwise, this I wanted to make this clear. So but I think you should be okay. So it's not, you should have time. You should have time to finish it. Any questions so far? So any questions about the assignments, but also about like previous material. So Bayesian statistics, what we've done so far, probabilities, before we start. Nothing. Any questions on Zoom? Can everyone hear me well on Zoom? I heard there was last time there was the quality of the audio was not great on Zoom. So.
Yes, we can hear you, but you can make the microphone come
Okay, I can try that. Let me try. How does this sound? Oops. Do I have to set this to 0, right? To mute this. How does this sound? Can you hear me now?
Oh yeah, that's much better.
That's much better? Okay.
Yeah.
Great. So in that case, I'll use the laptop, the microphone on the laptop from now on. Yeah. If you, I might be moving around the classroom, so if you don't hear me well, do write on the chat. And you can ask questions from Zoom as well. You can even, if you have a question, you can unmute yourself and ask a question. So when that's also possible. So I want to engage people on Zoom more. So do ask questions if you want. Okay, so let's get started. Now, why does this? It was just working. Okay. Yeah. So we just started briefly talking about linear algebra, like last session. So going super briefly, we know what a matrix is. We know what a vector is. So essentially, a matrix is an array of many numbers with the multiple column vectors. Again, a vector is a one-dimensional array. Matrix, 2 dimensionals. In general, a matrix, I want to give you a bit of intuition about linear algebra, because there's a lot to say here. A matrix encodes a linear transformation of something to something else. So the transformation has to be linear. It can be a translation, it can be a rotation, and so on. So these are kinds of transformations that we can do with matrices. They have to be linear or sharing, so or even shearing, for example, if you move like that. So these are kind of transformations. They're always linear. So for example, if you have this matrix here, which is 4 by 4, so the first column corresponds to the axis x, the second column to y, and the third column to z. And basically, we can encode things like translations. For example, if we, for example, using this column on the fourth column on the right, we can move things to the left or to the right. We can encode rotations with these numbers here. We can encode scale with the diagonal entries. So this number Sx will scale across the x-axis, this one across the y, and this one across z, and so on. So these are the kind of transformations we can do with matrices. We cannot do non-linear transformations with matrices. We cannot do that. So, of course, we spoke about earlier, to differentiate from a scalar, we use bolded x. We discussed this in previous slides. An element I is denoted as xi. An element is a matrix is denoted as ij. So this is row I, column j. So these ones here. The jth column is denoted as an aj. I wanted to highlight this notation. So when we talk about a row, we actually take a vertical vector and transpose it to make it horizontal. So basically, if we want to talk about horizontal vectors, we always use a vertical notation. We always start with a vertical vector and then transpose it. So this is what we're going to use throughout the lecture, and this is actually a standard in a linear algebra and in machine learning. So we will transpose to get horizontal vectors. Matrix multiplication. Again, really simple for Cij. If C is a product of A and B, then element I, location J, is sum over Aik Bkj. So we sum over the kth row and in the first matrix and the kth column in the second matrix. Inner product is the result between a vertical. This is a horizontal vector x transpose and a vertical vector is a scalar. So horizontal with vertical is a scalar. Vice versa is always a matrix. So that's the outer product. The outer product, if you flip them around, we always give you a matrix. So for example, this operation is not commutative for these kinds of, like in these kind of spaces. So we cannot commute these things around because we get different results. We can also write so Ax again, if we multiply a matrix A by a vector x, we get a vector, a vertical vector as an output. We can also write it like this. So each of these elements in the vector is the inner product between the column 1 in matrix A and X and so on. So basically each of these is scalar, 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 and together they make a vertical vector. Matrix multiplication has two properties, so they're associative like this, so we can first group A and multiply A and B together, or B and C. They're also distributive, so A times B plus C is equal to AB plus AC. So very, very simple. It is not, I have to say, it's not commutative matrix multiplication. So AB is not equal to BA. I should highlight that. Operations, so if you multiply identity matrix with A, we get the same result back, we get A. Vice versa, we can flip this particular one when we multiply with I by A. We can flip them around, but generally that's not the case. A diagonal matrix is defined as such. It's basically all the elements outside the diagonal are 0 basically, and we again these matrices are very easy to work with. So sometimes we will really like diagonal matrices. For example, when we do eigenvalue decomposition or singular value decomposition, the matrix we get in the middle is a diagonal matrix, and that's really easy to work with. We can multiply it super easily. We can calculate its inverse very easily. So we like diagonal matrices. So transpose operator, again, this flips the matrix around the diagonal. Basically, if you have a matrix on the diagonal, it flips on the other side. If you do the double transpose, you get back the same matrix, and so on. So if you multiply A times B transpose, then this is B transpose A transpose. So this is something I'd like you to remember but I'm sure you'll be familiar with this. A plus B transpose is equal to A transpose plus B transposed. Okay. The trace of a matrix, this is the sum of all the elements along the diagonal. So the trace of a matrix A is equal to a trace of a matrix of A transposed. Trace has some very nice properties. So trace of A plus B is equal to a trace of A plus trace of B. If you have a constant that we multiply by a matrix, this constant can come in the front of the trace. So we get that. Vector norms and matrix norms. So again, a quick recap. So I'm sure many of you will have seen most of these. This is a second norm of, we have a vector here, x. Again, this is a vertical vector, but here doesn't matter. The second norm of the vector is basically the sum of all the squares of each along each dimension of x. So x1 squared plus x2 squared and so on, and then we take the square root of that. And that's the second norm. The Euclidean norm is also called. We can also write it much more easily as x transpose x. So if you see this notation, often in derivations and so on, x transpose x, you'll know this is the square norm, the norm of x, the second norm of x squared to the power of 2. This is the first norm. The first norm of a vector is the sum of absolute values of x. Infinity norm is the maximum of all these absolute values. So we can take each one of them in turn and take the maximum, whichever one has a maximum in absolute value. And then the p norm is basically a general form of the norm which can encompass all of these, but many others. So if you set this p norm is basically the sum of all absolute values to the power of p, everything to the power of 1 over p. So we can get the second norm from this formula, we can get the first norm, we can get the infinity norm, and many in-betweens also. P can be rational, so it can have a norm of 0.5 or 2.3 and so on. It can be any positive real number. Everything clear so far? Yeah. There's a lot of properties about these norms that we won't go into details. Like, for example, they can create metric spaces, they're called. So if you study some of these more like math courses, you can study metric spaces. So you define a norm on the space with vectors and so on. They have the triangular property, so they obey the triangle inequality and many other things, for example. But we're not going to go into details over these. You can study these in more like an applied maths course. This final equation, this is the Frobenius norm of a matrix. So now we're talking about a matrix, not just a vector. So we also want to be able to take a norm of a matrix. So here A is a matrix. And the Frobenius norm is simply given by this equation. Again, you take all the elements in the matrix and we square them and sum them together and take the square root. this is also equal to the square root of the trace of A transpose times A. So we can also write like that. And if you do the multiplications of A transpose and A and take the trace, you will find that you get this form basically. But the reason why this is much succinct to write. So again, we'll use some of these forms in derivations. Perhaps like yes, let's see for SVM, for example, like some of these stuff we'll use this notation. Yes.
How do we use the trace of a matrix?
How do we use it?
Yeah, like why is it something a component that we need to know?
Gosh, I'm trying to let me think. What are the applications of a trace? Any ideas of some of you? When? Yes. Yeah. I'm thinking of something more like intuitive, kind of. Yeah, like yeah.
I use this as a trick in order to double check the characteristic equation. The coefficient of the square term of the characteristic equation can be the trace of the matrix, so it's going to save us a lot of kind of time calculating by hand instead of double checking that real fast.
Yeah. So this is in the characteristic polynomial of a matrix, right? Yeah, you can take the trace. Yeah, yes. So that's one option. So the characteristic polynomial is when you take the determinant of A minus lambda I, and where lambda is the eigenvector, take the determinant, and then you get a polynomial, and you can solve for the eigenvalues, and that's where you can use the trace. So I'll think of more. I have to think, but it's very useful. So the rank of a matrix now. So let's talk a bit about ranks. So a matrix generally gives us a set of linear equations, or also like linear vectors. Basically, we can think of the columns. We can think of the columns of the matrix as these vectors. And some of these vectors can be linearly independent. There's this concept of linear independence, which means that we cannot derive one vector from the set of all the others intuitively. So I'm not going to go into linear dependence, but you can read on that. Essentially, we cannot derive through a linear combination any vector from the others. So in that case, so this is linear independence. Now, if all the vectors in the matrix are linear independent, then the rank is full. The matrix has full rank. So for example, if the matrix A is n by n, then the rank of A will be n. If for example, only 7 out of 10 vectors are linearly independent, then the rank will be 7, for example. So that's the rank of a matrix. It's how many vectors are linearly independent. This is important because if a matrix is not full rank, we cannot take the inverse of it. We cannot compute the inverse. So the inverse only exists if the matrix is full rank. And if it is full rank, we can compute the inverse. And this concept called an inverse matrix, A minus 1. So when we multiply A minus 1 by A, then we get the identity matrix. But not all matrices are invertible. Again, they have to be full rank. If we take the inverse twice, we get back A. A times B inverse is B minus 1 times A minus 1. Questions? Okay. So briefly, I'm going to give you this is the equation of the eigenvalues and eigenvectors. So and we'll be using this in PCA to do principal component analysis shortly, but this is basically the eigenvector and eigenvalue equation. If we have a matrix A and the vector x equals lambda x, this basically x is called an if we find a set of vectors x's and lambdas that obey this equation, then these are called x's are called eigenvectors and lambda are called eigenvalues. But what does this? I want to give you a bit of intuition. What does this mean? Because I'm sure you might have seen this. An eigenvector is basically it's a vector that when transformed by the matrix A, it gives us back the same kind of vector collinear to the original vector x, but maybe just scaled by lambda. So here we essentially get back after applying this operation. So sometimes the vectors can move and can through a linear operation, and then they won't be collinear anymore. But when for these eigenvectors, the result will still be a vector, the same vector x, maybe just scaled more or less, or even going the other direction, but it still be collinear, entirely collinear. So this is the key idea. We'll see an example shortly. So generally we have this concept that the eigenvectors can form a basis for the space and so on. It's basically the space that can be spanned by the matrix and the operations. We can also think of the matrix. Let's phrase it in a different way. We can think of the matrix A as doing a projection operator also, for example. So then, after we apply the projection to another space, the eigenvectors will give us the subspace that will result from that projection, basically. So that's another way to express these concepts. So briefly, eigenvalue decomposition. So this is essentially when we have a matrix. Sometimes for these matrices, which are very complicated, it can be quite hard to work with. For example, it's hard to invert them. It's hard to multiply and do operations. It's much easier to do operations when we have diagonal matrices. If the matrix would be diagonal, that would have been super, super nice. But oftentimes they're not. So then it's hard to do all these things. So one way, what we can do in some cases is we can do these decompositions of the matrices. So then we can, if A has a complex set of transformations, then we can decompose that into much simpler transformations. So for example, if we can first do what is called like a projection into the eigenspace with Q, then we do we multiply. It's the other way around actually. You start from the back. So we do projection with Q minus 1. Then you scale with matrix lambda, which is the matrix of eigenvalues along those directions, and then you rotate back or project back to the original space with the matrix Q. So it's kind of decomposing the transformation into multiple transformations that are much simpler. So Q minus 1, lambda, and Q are much simpler transformations. And I thought I had. Well, I put it there, but I should have put this image also on the previous slide. So ignore the text. So just look at this image. So we have a matrix. We have this particular set of vectors. So you see, initially when we have a matrix M, then we first do a transformation with this other matrix V. So we rotate it, just do a rotation, nothing more, of these vectors. Then we scale them with the matrix sigma. This is the matrix of those matrices of eigenvalues. Do not look at the text for now, so I'll go to that. So when we scale this, we basically, you see how we compress the y-axis here. So this becomes much more compressed. So sigma 2 is this singular value or eigenvalue, basically, and it got compressed on this dimension. But this one is fine. This one stays the same. And then we rotate back to the original orientation. So this is how. So matrix M initially, or A, was doing everything in one go, but now we can decompose into several simpler transformations. So that's the idea. So for now, just that's the idea with eigenvalue decomposition. It's the same idea. So I'll put that graphic on this slide as well. So and basically a Q is simply the eigenvectors of the matrix, and lambda are the eigenvalues. So it's a diagonal matrix that has the eigenvalues on the diagonal. That's it. So, and we can do this only if A is square and also diagonalizable. So, and it's a concept, so I won't go through it, but you can read online what diagonalizable means. So, yes. So, singular value decomposition is it's literally a more general type of eigenvalue decomposition. It's more general. So you can do SVD for a singular value decomposition for any matrix. It doesn't have to be square or diagonalizable. So, but otherwise, it's basically the same. And for those matrices that are squared and diagonalizable, you will get pretty much the same decomposition. So, if you do it right, so as eigenvalue decomposition. So here with SVD, we have the same thing. We have a matrix that is not squared anymore. It can be n by p, and is decomposed into 3 transformations again. So remember, we start from the back, because when we apply this, we first apply through V. So we first apply V transpose, which is a square matrix p by p. Then we we scale with the matrix S, which is again a n by p matrix, and then we rotate back with this matrix U. And U and V are the eigenvectors of A transposed or A transpose times A. So it's almost like the eigenvalue decomposition, just a bit more general. And the singular values are the squares of the eigenvalues of A. So because we take the eigenvectors of A times A transpose, these singular values will be squared. Sort of like as we have. It's kind of like we have an A squared here basically. So then we get the squares of the eigenvalues. So we have to get back the eigenvalues of A, we have to take the square roots of these singular values. Otherwise, it's almost the same. Any questions? Yes. Say that again. I did.
Does the order matter?
The order of what? To matter. Like if we first apply V, then S, then U. Is that what you mean? It does matter. Yes. Yes.
I think there is written M equals U into sigma into V.
Yeah. So we do start from the back. Remember, so when this is the result of a product of three matrices, and we apply this. This is a big operator, for example, which composes three small operations. When we start from the back here, and we apply this to another vector, for example, x. So the first thing we do is multiply with v x with v, not with u. That's why it goes backwards. Does that make sense? Yeah. Yeah. Question.
Why does V transpose can do the rotation?
Why does V transpose why can V transpose do the rotation?
Yeah, does it mean the V does the rotation for to the original matrix? Does that?
It's essential. Let me say so essentially it's a decomposition into like a rotation, scaling, and another rotation.
So the function of V transpose is to do the rotation. Right?
Yes, exactly.
Yeah,
It's
so
just
I
yeah.
don't know how to understand this.
Yeah, so we can implement rotations with a matrix. So there are matrices that can express rotation transformations. We can just rotate something, for example. So we can do that.
So V is just the eigenvectors of A transpose times A.
Yeah.
And this product can do the rotation. The product.
Just V does rotation, not everything. Just V does one rotation. So you see, V does this rotation only. So you have a complex transformation. You first it's like you see how this transform. If you want to go from here to here, you have to do. It's complicated. It's kind of like you have to scale it along the x-axis like this, so the yellow has to become like that, and you also have to like elongate. So not just this kind of like rotation and elongation. So it's quite complicated to express it in one go. So you can do this complex transformation by decomposing into a series of smaller steps that are much simpler. So just basic, like more like rotations, scaling, and other rotation.
Is V a permutation matrix?
V is not a permutation. I don't know what you mean by permutation matrix. I know permutations in combinatorics, but
Is a permutation of the identity matrix?
no. So V is the matrix of eigenvectors. Some eigenvectors of this particular construct, A transpose A. These eigenvectors will be a set of it's an orthonormal basis. So it's a set of vectors that are orthogonal to each other. So then like they will basically these vectors just do a rotation basically of the matrix. Yeah. Question.
In the assignment, sir, when we're supposed to calculate the singular value decomposition of the matrix, the given matrix, the ultimate goal is to calculate that matrix A n by P that we have in there, and then we have to calculate the lambdas of this guy and then square root it, right?
The lambdas of you have to calculate the singular values of the lambdas of A transpose. Yes, so I show here. So exactly. So you compute the eigenvalues of A transpose using the standard equation.
which are different than the original.
which are different from the eigenvalues of A. Yes. Well, they will be almost there will be squares of that.
That's true.
Basically, but it's complicated because the A won't be necessarily a square matrix. So it's kind of but if it makes sense, it's if it is a square matrix, yes, it will be the same. Yeah.
Okay, so can we skip this part and then just conclude that the square root of lambdas that been calculated in the previous section would be accepted, or do we have to show all the work for this part, since the matrix is square, it's not rectangular?
You mean the assignment here?
Yes, sir.
Oh, let's talk afterwards about assignment. Yes, yes, about that. Yes, yeah. Okay, let's talk afterwards. Okay. Any questions? Yes.
Could you go back one slide?
Yeah.
So it says the singular values are the squares of the eigenvalues of A, and then on the next slide it says it's the squares of the eigenvalues of either.
Oh gosh, yes, there's a mistake. So, singular values. So is this one. So basically, so the singular values are the squares of the eigenvalues of A transposed. Basically, so I made a mistake. Yes.
And then on the bottom it says the square roots of eigenvalues of A transpose. Is by squares, do you mean square roots or like squares of the eigenvalues?
Yeah. So this is square root. So to get that. To get the matrix, so S, you will have to take the square roots of those singular values, basically.
Okay, so we take the squares and then we take the square roots of it, or
no? So you compute the eigenvalues.
And the result it gives you is the square.
The result is a square, so you'll get sigma squared. So you get the square root to get it.
So A transpose gives you a squared value.
The squared, yeah. So A transpose gives you sigma squared.
I see.
So you have to compute sigma. So maybe I'll rewrite it to make it with sigma squared. Yeah.
So singular values are just like eigenvalues of A and A transpose, or is it square of?
Yeah, I think some people refer to like one or the other. I know like even there's a bit of confusion. Like usually are the square roots of the eigenvalues. So it will be a sigma will be a singular value, but you get sigma squared when you solve. When you solve for this, you get sigma squared. Sigma will be the singular value. Yeah. Yeah. Okay. Moving on. So this is, for example, this is an example of for example, how SVD looks like for a simple matrix like a 2x2. So we get so we first get a matrix of eigenvectors. We get this is U. This is a matrix of eigenvalues or singular values, I should say, and this is like another matrix of the inverse matrix of the eigenvectors. So this was the best example I could find also online, but I'm still not happy even with this, because normally you normalize these vectors, for example, to make them norm 1, but kind of like this example does not have them normalized. So I'll try to find a better example, like better picture. But I liked how they color coded it. So basically, so you can see it's a composition of 3 matrices basically. So that's why I still decided to include this picture. So that's kind of the idea. But generally, you would normalize these columns, and yeah. Okay. So matrix calculus. So we also have to like briefly recap. So matrix calculus. So again, super briefly, the reason why we need matrix calculus in this course is because later on when we talk about neural nets, for example, we'll do gradient descent and backpropagation, and that requires computing derivatives, and computing derivatives with respect to vectors. So these are uneven matrices and so on. So these more complex objects. So that's why we need. So we have a function, and we take the derivative not with respect to a scalar, but with respect to a vector, for example, or even a matrix. So So here's for example derivative with respect to a matrix A. So we simply have a function that takes as input a matrix and goes to R. So and returns a scalar at the end. So if we take the derivative with respect to a matrix of this function, we simply get a matrix of derivatives. So it's derivative of f with respect to the first element of the matrix, a11, a12, and so on. So we get the whole matrix of first derivatives for this particular example. All good? Then we can take the same thing with respect to a vector. So we have a function that takes as input a vector and returns a scalar. So we can and then again take the derivative with respect to a vector, and this would be the derivative of f with respect to x1, x2, and so on. So so here, for example, so in machine learning, for example, f of x could be a loss function. So you have a neural network, you have a loss function that computes the error, the prediction error of your input. So x here could be again like a range of inputs. For example, for a particular person, could be the age and so on, like income or other things, and you predict it and so on. Or for a house price evaluation, you have the house size and so on, and like the year it was built and so on, and you can predict the price of it. So that's why so f this again will be super important, and we'll use this when we study neural nets. So and the Hessian of a function now. So this is different from what I was talking earlier about the derivative spectrum matrix. So the Hessian of a function f. So this is a function again that takes as input a vector in Rn and returns a scalar. So this is the matrix of double derivatives. So this is we're taking now with the Hessian, we're taking the second derivative of respect to each element. So we get basically we get a matrix, and on the diagonal we have the second derivative with respect to the first dimension x1, x2, and so on, xn. And off diagonal we get any combination of first derivative with respect to x1 and x2 and so on. So we get all the combinations of derivatives between xi and xj. We'll use, for example, the Hessian in optimization. For example, there's algorithms that rely on the Hessian to perform to optimize a particular function. They compute it. It gives us an idea of convexity and concavity. So if a function is convex or concave, we can get that sort of like information from the Hessian matrix. And many algorithms use this to make the optimization much faster. So there's second order optimization methods that use this concept of the Hessian to get a much faster sort of convergence to your suitable parameters. So this is the Hessian. So so let's talk a bit about principal component analysis now that. But let me before again we move on. Any questions about matrix calculus, Hessian, first order, second order derivatives? Okay. Any questions on Zoom? Thinking if we should take a break now or go for a few more minutes. Let me see briefly. So let's go for 5 more minutes or 10 more minutes, and then we'll take a break. Okay. Okay, so principal component analysis. So how many of you have run PCA before or have heard of it? Or okay, some of you. So essentially, it's a principal component analysis is basically a method that's been heavily used in machine learning. So this is a classical method. This has been used for like a very long time, and this is even before like for example, deep learning was around and so on. And it was mostly used to do dimensionality reduction, to reduce dimension of our data, and to basically select key features. And this is also equivalent to selecting key features from our data that are more informative. In general, in many applications, the data is highly correlated. For example, if you have an image, all the pixels, the nearby pixels, are very correlated with each other. So the intrinsic dimensionality of the data is much smaller. So that's also called the manifold of the data. So we can do something like PCA to reduce dimensionality to make it much simpler. So to then be able to pass it to a machine learning model and actually learn much faster from a reduced dimensionality. So you can see, for example, in this example here, there's a 2D data set. If so the data is expressed, of course, with x1 and x2. So we have two-dimensional points. We're given two features. And you can see how actually in practice this data kind of lies along this dimension. So then essentially this what we call principal component will basically capture the data much better than this other principal component. And we'll see a bit more why that's the case. But the idea is that like a PCA would give us these new principal components, and we can project the data on these new components, and then this will become our new representation. For example, our new axis. So here the green axis will become our new basis, and we can do this with eigenvectors and eigenvalues. So we'll see how that goes. So one thing I wanted you to see here to note is that you see how. Actually, let me ask: why does the principal component one? Why is it like sort of better at capturing the data than the second one? So why is PC1 a better projection than PC2? Yeah.
More data points around the line.
Yeah, it has more data points around the line. Yeah, but more expressed in a different way.
I was talking about the overall distance from each point.
Uh huh.
If we sum all the distances, it's closer.
It's So I see. So we lose less information. We lose kind of like yeah. That's correct. Yes. What else?
Basically, the error will be less in case of PC.
Yeah.
Like we measure the distance.
Both of them are mutually exclusive because. Yeah. That's a good question. Yeah. So that's a good point. So even if we represent them in this basis, since they're two-dimensional, we still get two vectors. This new subspace with the green axis will still span the whole, so we can still represent them equally. I know in this example, yes, but imagine you have only one projection, like you only project on one, so you reduce dimensionality to 1D. So another thing which kind of linked to what we were saying is also the fact that if we project on PC2, for example, points that were initially far apart, so this one and this one, will all of a sudden project to the same spot, so then will become close together. But initially they were far apart. So that's another aspect too. So this is about the so we kind of we still kind of want to preserve with the points that were far apart. We still want it to stay far apart in the new projection. And generally, so how we can compute, for example, something like PC1 is by taking the argmax between this expression, y transpose x times x transpose y. But don't linger too much on that. We'll get soon to why it comes to that, for example. Essentially, we maximize the variance of the projection points on this vector. Essentially, this. So when we do this, x transpose y, we project a vector x, for example, or this is a whole matrix, so it's like we project the whole data set, but it's the same thing. We project it onto y. So we do the projection. So that's the inner product, does a projection from one vector to another. So this is what we mean. Yeah. So this is what I was talking about. So in general, when we do inner product between two vectors, that does a projection. So we have a vector x that is projected into another vector u. So then this result is a scalar, and this is the distance of the projection from I'm trying to see. I've never done this. If I can draw on the slide. Oh, I guess. So if we have a vector here, we have two vectors. This is x, and this is u. So here we project the vector x onto u, so we get so this essentially this distance will be this in a product. So that projection as a distance would be x transpose times u. Yeah. Okay. Okay. So let's do quick quiz. Well, which of the following options maximizes the data diversity? Which of the following projections? The one on the left or the one on the right? Left. Why? We're using what? Yeah. We're losing into the projection. Yes. Exactly. So we're losing with this one. We're losing much less of the original data, and also we still have the same property I was talking earlier. For example, these points initially were far away from each other, and now they get close to each other. So they basically this is not what we want. We want to preserve sort of the original distances between the points. So let's take a quick break, 5-minute break, and then we'll resume afterwards. Okay. Yeah.
Regarding the SVD problem.
Yeah.
So earlier you mentioned that we could use a calculator for part of the problem, and what I've done so far is I've taken like the transpose A transpose or AA transpose, and I used the trace, determinant, and minor of the diagonal to get the polynomial.
Yeah.
Is for this, could I use like a Desmos graphing calculator to just graph the function and then find the lambdas? Or
that's
are we
okay. That's okay.
expected-
That's okay.
Okay,
That's okay.
sounds good.
You can also get it like if you do it by hand, you can get some kind of square roots. You get something like imagine like 1 plus square root of 3 or something like that. So it doesn't look too bad. But yeah, don't worry.
It's okay to like approximate it.
It's
with
okay.
the
It's okay.
decimals?
Yeah.
Okay.
Yeah.
Sounds good.
Yeah. Okay. All right.
Cool.
Yeah.
Thank you.
Hi.
During singular value decomposition, we do A transpose, right? So
Yeah.
is that to convert the matrix into a square
Into square.
matrix?
Exactly.
If you have already a square matrix, do you need to do that process?
No, you can do that, but you can do that. It will still be a square matrix. It will still work. It will still work.
Change, right? For A transpose A, the vectors change compared to A. So
If you do, do you have a pen and paper? Just, or so if you try to do A transposed, like in terms of SVD, so if A becomes U sigma V transpose like this,
right.
or V V minus 1, let's say, but it's the same. They're the same because these are orthonormal bases.
Right.
So this is only one A. Then this will become literally U sigma V minus 1. Then A transpose will be V sigma U transpose.
Right.
So this cancel together.
Yeah.
So you get U
eventually-
sigma squared
Right.
U transpose.
Right.
So now this is basically your eigen decomposition. decomposition. But the only difference is this is a square matrix, but it's the same because those even when I was talking about. So you take it's a diagonal matrix, so the
Okay.
you get a square. So that's the same thing.
Okay.
Yeah.
Thank you.
Welcome.
It is fun,
Look at this. This is the one at TA. Oh, that's so funny. Look at that. That means people are because there only have like 17 or 18 students in that class. Oh, that's not that many. Yeah. Is it a graduate house or undergraduate?
Okay, shall we continue? Because we have a few things to go through. So we're talking about PCA and how we can project data onto a smaller dimensional space to then be able to do learning much faster. So so you see how we can project again from a 2D data to just a single line to 1D data. This idea generally, how it started was essentially people back in the 80s and even before was sort of like thinking about this idea of how do we project something to a lower dimensional space, but we still preserve as much variation as possible. This is the kind of the formal construct and formal way they were thinking about the problem when they first started talking about it and working on it. So more formally, we want to maximize this expression, which if you look closely at it, looks exactly like the variance expression. So remember the variance of x, of around the variable x, was expected value over x minus e of x squared. So so look at it. So this is expected value, the sum. So we sum over all the data points of x, which is projected now. So it's not just the original x, but also it's projected onto this vector u. So minus, this is the mean of the vector x, again projected on u. So this is e of x. So this is exactly the formula of the variance that we're talking earlier in statistics. So and everything squared, yes. So because we take the second moment. So the only difference now is that we have it projected onto this single vector u. And let's see, how do we derive it formally? So actually this is quite simple. So so in order to make these derivations easier, generally we can assume that the data x is centered. So centered meaning that again it's the expected value of x is 0. So this way it simplifies things. So in that case, this thing is 0. So the expected value of x when we talk about centered. So then we just have to maximize 1 over n times the sum of u transpose x n squared. And you can rewrite this as, instead of it being squared, you can rewrite it as an inner product between u transpose xn times x n transpose u. So this is, again, it's the transpose of that. So this one we took it transpose. So we can write it like that. But then we can apply associativity, and then we can decide to actually, instead of multiplying this and this, we can multiply the x's together. But remember now, if you look closely, this is not an inner product between xn and xn transpose. This is the outer product. Xn here is a row vector. No, xn, sorry, is a column vector. It's vertical, and xn transpose is a row vector. So this is a vertical with horizontal. This is the outer product. So we get a matrix here. So this whole thing here is a matrix. It's called a data covariance matrix between x and x. And we can move the u's on the outside of the sum here. So you can move this u completely outside, and this one also outside. And we just put the brackets here, so we can just do the sum over the x's only here. Because you see, n only comes in the x's, so u's are completely independent. So this whole thing becomes simply u transpose times the data covariance matrix, this whole thing, which is S, big S, times U. And what does this look like? This looks familiar, right? What? Yeah. This is the eigen decomposition. So which is also like SVD is just a general form of eigen decomposition. So look, this is. Remember, in eigen decomposition we had Q minus 1 lambda Q. So essentially it's almost the same. So here instead of a matrix, we just have a single vector. But of course, if we have a set of many, if we project on many vectors, we simply get a matrix here. So we can get replace this. You can imagine replace this U by a whole matrix of vectors we project on, and then we get the eigen decomposition. Yeah. And of course, we also constrain. So in general, with everything, we constrain these vectors to be unitary. So the norm of the Euclidean norm of U, so U transpose times U, which is also the L2 norm, has to be 1. So we constrain this. And another concept that I wanted to briefly sort of mention is the concept of Lagrange multiplier. So we can basically, when we try to maximize the function, and we have something, you see how we're trying to maximize U transpose SU. So this is from the previous slide. We try to maximize this. But sometimes we have a penalty, of course. We're trying to put this constraint. So essentially we add this penalty that if U transpose U deviates from 1, somehow, it's not exactly 1 it deviates, then we penalize with lambda. And lambda is called the Lagrange multiplier. It's the weight of the penalty that we apply on the constraint. And we can optimize this. And how do we generally solve this? For example, so one way to solve it is we take this function, we put it as a function L of U, as a function of U, and then we take the derivative. So the first order conditions are that we take this function and we take the derivative and set it to 0. And that's, and if we take the derivative of this with respect to u, what do we get? So we get something like, so you can think of these u's, maybe even for a second you can think of, so this is, wait. Okay, pen. This is an L of u. L of u. So this is an L of u. And if you take the derivative with respect to, oh gosh, here, this is L of u. And then if you take the derivative with respect to u of this loss function, then we basically, this term is kind of like an SU squared. So if we when we do derivative of u squared, we get 2u. So basically there will be 2SU plus this is again another u squared, which becomes 2u plus lambda u minus lambda equals 0. So that we will remove the lambda, and we basically get this equation. So we basically get like SU is equal to lambda u. And we might have to get actually to flip the sign here. So we might have to do for this one 1 minus u transpose u. I cannot write well on my trackpad, but 1 minus u transpose u. So we might have to flip the sign, but it doesn't matter because lambda again is a scalar, can be. So from this, we simply, if we take the derivative of this function L of u with respect to u, we simply get SU plus minus lambda u equals 0. And then this is SU equals lambda u. So this is the equation of the eigenvectors and eigenvalues. So then we get that u is an eigenvector. So the vector that maximally maximizes this variance u is the eigenvector of the data matrix. Of course, we want to do more than just one vector. Sometimes we want to project on multiple vectors. So then what we can do, for example, we can compute all the eigenvectors and take the top most important ones, for example, with top k. And here we select the top k by looking at the eigenvalues, and we select whichever vectors have the largest eigenvalues, and those will be the top k. So we can order them from the eigenvalues, and this way we can select the top k. And this is of course useful for many things. For example, for data compression, for example, we can compress the data, and when we send it over the internet, we can do all kinds of things. In machine learning, we do it to make the learning much faster, because we can. This is a pre-processing step, and then we pass this reduced dimensionality data to the ML model, and it will learn much faster. Let me erase this. Yeah. So yeah, and of course, so we're talking about this. When we project with PCA, the new features will be so. Let's say we project over k vectors. The new features of a data point x would be all of these. So x projected onto u1, x projected onto u2, and x projected onto uk. So those will be the new features that will become the new x basically in this new representation. Does it make sense? Questions? Okay. So for example, if we actually apply them on a type of data and we do a plot, we order the eigenvalues from the largest to the smallest. This is the kind of stuff we get. We can basically order them by the size of the eigenvalues from the largest to the smallest. And for example, we can decide to just take the first 10, for example. We can see that after the 10th eigenvectors and eigenvalues, then the rest do not capture that much of the data. So essentially, we can say that the intrinsic dimensionality intrinsic to this data set is around, let's say, 10 or around then. I'll skip some of this. Here, So here the key idea is, of course, people have been applying this to faces, and this is actually called eigenfaces in literature. So when we talk about face images, again, your X is an entire image that basically is represented in this way, and we can compute, for example, these are the eigenfaces. These are the principal components that we obtain from a data set. So this is the first component. This is second. So this is the first principal component, first eigenvector, second eigenvector, third, and so on. And you can see how, the first one is kind of an average face, and then they kind of become more quirky. And this was used, for example, in one of the first and earliest applications of ML. For example, for face detection. For example, they would compute some of this. They would project this on a face image onto one of these onto these eigenvectors and try to find if it's actually an eigenface a face or not. So and of course, there's also something people were doing this also with Fourier transforms. If you take if you have an image and take the Fourier transform of the image, you can also the Fourier transform gives you a representation of the image where the center of this Fourier transform essentially has like low frequencies, and basically those captured like the kind of like overall global features. So and of course, if people were talking about basis sets, for example, these sinusoids, these kind of like elements that are in the center of the Fourier transform. But kind of when we do we can do these eigenfaces and eigentransformations, and we get these eigenvectors on the faces. They kind of represent also like a basis set. They create again a basis set with which we can reconstruct a particular image. So if you have, for example, a basis set of just 4 eigenfaces or these eigenvectors, then we can reconstruct an original image. For example, this one. So we add all these projections basically, and we reconstruct back the original image. So from these linear combination of eigenfaces. Does it make sense? So now, and I should highlight the new representation we have for a particular image will be this one. Will be, for example, just a vector of 4 elements. So we go from like having 500 or 500,000 or 1,000,000 pixels in this image to just 4 values. And those will be the weights on all of these eigenfaces. So that's a huge compression factor, for example. I'll briefly skip this, but the idea here is that I won't go into details in this plot, but the idea was that if we have these new images and data points, this is the space that is spanned by the eigenvectors U1 and U2. So you see, this is a space, and we project them, and we find again. This is how they were finding, using it to in these earliest applications. They were projecting them these images onto the space, and we're trying to see how close they are to for example, some categories. If this is a male face, a female face, and so on, and these will be classes. So then they could do the classification. So you see again, if we project a face of a person, this works. A face of another person, it works. When we project a flower, this doesn't work that well. So it kind of this is how they could do face detection. I'll skip this for now. Let's do a quiz. How about that? Yeah. And I kind of do a recap. So join that. Okay. Yeah, you can also use, if you just go to joinmyquiz.com and put this code, that should work, I think. Try that. Okay, everyone joined? Are we all ready? Anyone who's still joining? Okay, someone waiting. I see some people. So I thought it would be nice to go through these quizzes, sort of to recap the material and kind of like also like discuss a bit about the concepts. You can even speak to your neighbor if you want to consult on something. So we can do all of that. Okay, are we ready? Okay, I'll start. So we're starting in 3, 2, 1, go. So which of the following are true statements for any matrices A, B, and C? Mark, will that apply? $15 seconds left. 7 seconds left. 5, 4, 3, 2, 1. Was that good or bad? So, let's see. Okay. So people voted the first two. So what about the first one? So this one is, what was it called again? Associativity? Yes. So matrices are associative. Matrix multiplication is associative. Are matrices distributive? Does it apply? Yeah, it does. Does the inverse exist always? No. What are requirements for inverse to exist? Does anyone know? Full rank. Yes. 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 Full rank. So they have so for the inverse to exist, the matrix has to be full rank. It has to have a full set of independent, linear independent bases. Yeah, vectors. AB equals BA. Is matrix multiplication commutative? No, it's not. Okay. Next question. So we have, we'll have a few. Ready? Okay. 3, 2, 1. So what is going on here? So you have to draw the set of all the points where the one norm is equal to 1. So don't draw them as vectors. Draw the contour. Yeah. Remember the one norm? It's the sum of absolute values. Think about it. You have 3 minutes on this one. It's longer. You can take a few points and try to compute them even on paper and see how they would get. How's it going? Yeah. You submitted, yeah. You have to yeah, you have to draw your response, yes. And you have to draw it on that plot and then submit it. Yeah.
I wasn't sure if it automated.
Yeah. So again, you can assume that that whole box is a -1 to 1, from -1 to 1. So it has to be within -1 to 1. 38 seconds left. How's it going? Good? Yeah? How's it going there? You good? So again, you can discuss with your neighbors on these questions and consult. Okay, 8 seconds left. Submit your response if you can. Time's up. Okay. I wasn't expecting that. What do we have here?
I have zero doubt that Emily is right.
How can we die?
Yeah.
Only one proper S curve here.
I saw some correct responses, but I love the spiral. We have a Gaussian distribution. We have a cumulative density function. Linear, yeah. This is the plot of the first norm. This is interesting, yes, but yeah, this wasn't the solution. So let's take this example. So this point, so this says that all these points on this line have norm 1. Does the origin have norm 1? 0, 0. So the norm at 0, 0 is just 0, right? So it cannot be this one. What about a straight line like this? Again, it passes through 0, 0. So the point at origin always has norm 0. It doesn't have norm equals 1. This square here again passes through origin. This point here in the corner, well, it kind of hides. This one in the corner here would have 1 plus 1 would be 2. So that would be norm 2 here. So in this particular corner at the very top. Circle, that would be norm 2. So for example, so this is the correct answer. So you see here. So this it's a diamond that goes from a -1 to 1 on all sides, basically 1 to -1 and like that, because So this is a correct answer. So this diamond here, this diamond, so all the diamonds have norm 1. These are all the contours. These are all the points that have norm 1 equals 1. And this, yeah. So I'm glad to see. So for example, so these are all the points that have norm 2 equals 1. This is a circle. This is also called the unit circle for norm 2. Does it make sense? How many of you understand the solution? What's is it still unclear? Okay, so most people got it. Well, I love the yes. Okay. Okay, so let's go to the next question. Nice. Okay, next question. Ready? 3, 2, 1. So you can write keywords, succinct keywords, for example, or like even a short sentence. No, nothing too long. Oops. How's it going this way? Yeah. Good? Yeah? How's it going? Submitted? Nice. Nice. Yeah. Maybe I get too much time for this one. Okay, 15 seconds left. Three, two, one. Okay, let's see the answers. The derivative is continuous at 0. Very good, yes. Computationally efficient. Why computationally efficient? Satya Prakash? L2 is more stable. In what sense more stable? So let's take them one by one. So at 0, indeed, L2. So L1 looks like this. So it has a right acute angle here at 0. L2 is round. So it's basically so it's the derivative is continuous. So essentially, and And what this means is that for optimization problems, the second derivative is that derivative being continuous is can often be important. So that's why some people prefer the L2 norm, because at 0 the derivative in L1 is not continuous. Or I should say no. So I think the correct mathematical thing to say is that at 0 for L1 norm, at 0 the derivative does not exist. So it only in the limit exists, but not does not exist at 0. Optimization, less variance. So and there's more to it than just that. So there's also differences, for example, between L1 and L2 in terms of outliers. Which one penalize outliers more, L1 or L2? L2. Yes. So that's another difference between them. So if you have outliers, L2 will penalize them more. You may or may not want to do that. It depends on the application. Mean distance between error is better preferred. Stranger regularization. Stronger regularization. L1 can So it is in some respects, but you can control that with the weight as well, the regularization with strength. So L1 can deal with sparse features. Yes, it's closer towards sparsity. So the more you come down in the p norm to p equals a half, for example, or the 0 norm, for example, p equals those are kind of sparse. They get closer and closer to sparsity. So yes. You didn't understand that? Yes. The sparsity, yes. So if you take the 0 norm, L0, that one basically counts. So you raise the numbers to the power of 0 to the power of 1 minus 0. It's not well defined, but how it is normally defined, the 0 norm, is that you count if one of those dimensions is non-positive. So if it's non-positive, then it will have like am I correct? Actually, I'm trying to remember that this is out of my head, but I think this is the correct answer. Like if any in the audience remember the 0 norm. No. Essentially, it counts how many non-zero features you have. If I remember correctly, this is so the 0 norm. So that's a measure of sparsity. If your data is sparse, so it has many zeros, it will not add to the norm. Basically, that's what it means. We can discuss also in the office hours and look on the proper definition, but the L2 norm fits the data better. It is more specific to the data. Yeah, it depends how the data was generated. If the data was generated with Gaussian error, Gaussian noise model, then yes. But if it was generated with a different kind of like a noise model, then probably no. So it depends, yes. But I think it's a good point actually, because most data in nature has Gaussian sort of noise. To remove the outliers, yes, that's a good point. Yes, that's what we were talking about earlier. The L2 norm, we get positive and negative both ranges. It's always positive. I'm not sure what. Yeah, every norm is positive. It's always it's a distance function, so they can never be negative. L2 is generally seen as more accurate. Okay, let's move to the next question. We have like 2 or 3 more, but let's see how many we can do. Are you ready? So you can talk with your neighbors again, if you don't know. I'll leave this one, leave these on for this question. Let's see what we get. Some dimensions provide little value. PCA can focus on the important dimension, increasing computational efficiency. Adding too many features for classification can reduce model accuracy. High dimensions require exponentially more compute resources than PCA can reduce the dimensions. PCA reduces dimensions focusing on the important information. A very interesting point about visualization. To make it comprehensible. So indeed, it can be used for even for visualization with PCA, so to help us visualize better. Too few data points and too many features. More data diversity. Balancing model distance from data points in each dimension. PCA helps by maximizing diversity. PC can help linearize the data. Millions of dimensions is the curse of dimensionality. PCA takes the most important dimensions that represent most of the data. 10 seconds left. Time's up. So yes, so all of these answers were great. All of these were really good. So I like it. I love it. So PCA, again, we have millions of dimensions in many data sets, like images, for example. A single image, a megapixel image, has 1 million pixels. If you have a color image, then you have 3 million, because you have 3 channels for each pixel. So you're talking about millions of dimensions. And PCA can help bring that down a lot. So otherwise, it would be almost impossible to, unless you use some other inductive biases to learn right away from all those millions of dimensions. And the curse of dimensionality, so think of it also about those matrices we're building, those covariance matrices. If you're studying covariance between all the pixels with each other, so you're talking about a million pixels by 1 million pixels to study all the relations between them. So you're talking about a matrix that is 1 million by 1 million, which you cannot even represent in a computer. Basically, it won't even fit, or it will be very hard to fit in your memory. So that's the curse of dimensionality. It's as it increases, the dimensions generally explode. Some algorithms can be n squared in the complexity and so on. So PCA can help bring that down. So then it would only bring down to 5 dimensions, 20 dimensions, and so on. That's much easier to handle. Okay, do we have time for one final question, or yeah? Do you want to, or you want to, yeah? Okay, one more question. Ahead. So which of these lines preserves the variance, most variance in this data set? 15 seconds. Yeah. So. Okay, almost everyone got it. Yeah. So the continuous line. So here, so you see in this question, you can see actually the projection, the data projected on each of these axes, and you can see how on the C1, on this one, it's much more spread out than on C2 and C3. So the answer was C1 here, this axis. Does it make sense? Yeah. Okay. I'll see you on next week. Have a nice weekend.